Today we're going to begin the next part of this chapter on polynomials and talk about factoring. And we're going to start with a specific type of factoring called factoring the GCF. Before we can get to factoring the GCF, we need to be able to find the GCF. So a little background. Prime numbers are whole numbers that can only be divided by 1 and themselves. For example, 2 is only 2 times 1. 3 is 3 times 1. 5 is 5 times 1. 7, 11, 13. All the primes are odd except for 2, and you know that some odd numbers are not prime, like 9 is 3 times 3, so it's not prime. If a number is not prime and it's a whole number, it will be composite. Composite numbers are whole numbers that have factors other than 1 in themselves. 4 can be written as 2 times 2. 6 can be written as 2 times 3. 100 can be 1 times 100, 2 times 50, 4 times 25. There's more options. It could be 10 times 10. So those are composite numbers. What we want to find today is the GCF, the greatest common factor. It's the largest integer, variable, or term that can be divided evenly into numbers or expressions. For some of them, we can find the GCF just by looking at the numbers. For example, if I want to find the greatest common factor of 10 and 15, I'm looking for the largest integer that can be divided evenly into the numbers. So 10 and 15 are both divisible by 5. That is the GCF. 10 is also divisible by 2, and 15 is divisible by 3, but the greatest common factor, common means the same, factor means a number that divides into it, the greatest common factor is 5. If I took those numbers and wrote them as 10x and 15x, my GCF would be 5x. I look at the numbers, 10 and 15 have a common factor of 5. X and x, that x is common, so it goes in the GCF. We'll talk more about the variables as we go. To find the GCF, and we're talking about the numbers specifically here, one way to do it is to make a factor tree for each number to find the prime factorization and identify the common prime factors. The GCF is the product of all the common prime factors. So the smaller numbers like 10 and 15, you can just look at and find the GCF. As the numbers get bigger, you may need to make these factor trees and find all the common prime factors. Here's what it looks like, for example. 120. I'm going to just start factoring this. So it's even, so I know it's 2 times something. It's 2 times 60. And I'm going to keep factoring until I have only prime numbers. 2 is prime, so that branch is done. 60 is 2 times 30. And I have options here. 30 I can either write as 2 times 15 or 3 times 10. It doesn't matter what I pick. 10 is 2 times 5. And if I look at the bottom of all of these branches, 2, 3, and 5 are all prime numbers. So those are my prime factors. 128, I'm going to make a factor tree for that. It's 2 times 64. 64 is 2 times 32. And then again, I have options. I can do 2 times 16. I can do 4 times 8. It doesn't matter as long as you keep going until the bottom of each branch is all prime numbers. That's my prime factorization tree. The greatest common factor is the product of all the common prime factors. What that means is here I have a 2. I have the same prime factor in my other tree. So I'm going to look for pairs in the trees that are the same. This 2 has a match over here. This 3, there's no 3s in my factor tree for 128. I have another 2. I can match that up with another 2. So if I look at these factor trees, there are no other prime factors that should be circled. So my GCF is the product of all the common prime factors. Once you circle in both trees, look at just one of them. I have a 2, a 2, and a 2. My GCF is 2 times 2 times 2, which is 8. Try another example. 81 is 9 times 9, and each of those can be factored to 3 times 3. 54 is 9 times 6. 9 is 3 times 3, and 6 is 2 times 3. If I look at the bottom, all of these are prime numbers. To find the GCF, I'm going to look at pairs that are the same in each tree. So a 3 here can pair up with a 3 there. This 3 can have a match in the other tree. This tree can have a match. Nothing else is the same. So my GCF is 3 times 3 times 3, which is 27. Now, some of you may know that 27 is the largest number that divides into 81 and 54, and that's great. But the prime factorization gives us a way to do this for all problems. Let's look at some examples with variables. Here I have 3x and 15x squared. When I do this, I'm going to look at the numbers first. I have 3 and 15. Now, if one of the numbers divides into the other number, that will be the GCF. 15 is 3 times 5. So the 3 is the common number. The biggest number that both 3 and 15 are divisible by is 3. Then look at the variables. I have an x over here. And then the 15x squared means x times x. So there's one common factor of x. My GCF includes the number and variable that are the greatest common factor. Over here, I have 21x squared. So that's 21 times x. And 49x to the fourth, x times x times x times x. 21 is 3 times 7, and 49 is 7 times 7. So what's the same in the numbers is the common factor of 7. So when I go to write my GCF, I have a 7. Then I look at the variables. X in one factor can match up with an x in the other factor. The next x's can match up. Now there's no other x's to pair up with these. Therefore, I have circled everything that's common. So I look at one of them. I have x times x, which is x squared. Now, there is a shortcut for doing this with variables. The GCF for variables is the variable with the lowest exponent. So in this example with the 21x squared and the 49x to the fourth, I had an x squared and an x to the fourth. The squared is the lower exponent, so the x squared is what goes in the GCF. Couple more examples. Here I have 80x squared y and 36x squared y cubed. So I'm going to split up the 80. Let's say it's 4 times 20, for example. And again, you have options here. This is 4 times 5, and that's 2 times 2. I keep going until all the bottoms are prime numbers. 36 is 6 times 6, which is 2 times 3, and 2 times 3. Then I look for what's common in those numbers. Find the pairs that are the same. There's nothing for these 2s or 5s to match up. There's nothing for those 3s to match up with. So my GCF is 2 times 2, which is 4. And then I need to look at the variables. I have x squared and x squared. The lowest exponent is x squared. I have y and y cubed. Y is just y to the first. So my lowest exponent is y to the first, or just y. So you don't really have to do outwork for the variables. You just look for the lowest exponent. One more of those. 45 is 5 times 9, which is 3 times 3. 18 is 9 times 2. This is 3 times 3. So my GCF, I need to circle the factors that are the same. There's a pair of 3s and another pair of 3s. 3 times 3 is 9. This is a pair that you may be able to look at again and see that 9 is the biggest number that goes into them. That's fine. I look at each variable. I have an x here, but no x there. There's no common x's, so it doesn't go in the GCF. I have y cubed and y to the first. The lowest exponent is the y to the first. We can also find the GCF of 3 or more terms, and we do it the same way. Take each of the numbers and make your prime factors for each one. Here I'm splitting up 36. 54 is 6 times 9, 2 times 3, and 3 times 3. 60 is 6 times 10, just 2 times 3 and 2 times 5. But here's what we need to do. When we go to find the greatest common factor, it has to be factors that are common to all three. So if I circle a 2 in one of these trees, I have to be able to circle it in all three of them. I have a 3, a 3, and a 3, so that's common. Here I have a 2 and a 2, but there's no 2 in the factors of 54, so I can't circle that. 3, 3, no 3. Nothing else is common. It's only the numbers that you can factor and you find in all three of them. 2 times 3, my greatest common factor is 6. Last one, 16x squared. So 16 is 4 times 4. 12 is 3 times 4. Oops. Just 2 times 2. And 20 is 5 times 4. So if I look at what's the same, I have a 2, and I have another 2. Now, some of you may have looked at the beginning and said, oh, the only number, or the biggest number that goes into 16, 12, and 2 is 4, and been able to find that right away. Then I look at the variables. I have an x squared, an x, and no x. The lowest exponent is the no x, so there's no x's in the common factor. It has to be something I can take out of all of them. For today, you're just going to find the GCF. Starting tomorrow, we're going to factor out the GCF.